Hello, everyone. Welcome to Toronto Machine Learning Society's annual conference. My name is Aarti Malhotra, a PhD student at University of Waterloo, and I'm glad to be the moderator for this session. I'm honored to introduce Somnath Banerjee today. Somnath is the head of shopping discovery at Pinterest. He and the team are responsible for distributing personalized and inspiring shopping content across different surfaces of Pinterest. The team is spread across San Francisco Bay Area and Toronto, and is an expert in applying cutting-edge AI/ML techniques in content recommendation. Previously, he was a director of machine learning and the head of search quality for Walmart Labs. He has decades of experience leading machine learning teams at various organizations. He holds a PhD in information retrieval and has published a number of papers at prestigious conferences. May I now request Somnath to enlighten us about optimizing Pinterest shopping recommendations for purchases. If anyone has any question, please feel free to post in the chat. We will have a Q&A session after the talk. Over to you, Somnath.
Thanks, Aarti. Thanks for the nice introduction. Let me share my screen. Good afternoon, everyone. It is a pleasure to be here. My name is Somnath, and I will be talking about optimizing Pinterest shopping recommendations for purchases. Pinterest is well known for its recommendation. And in this talk, I will share how we are incorporating purchase optimization objective across various recommendation stacks with minimal changes. Little bit about myself. I'm the engineering lead of the shopping discovery team of Pinterest. I live in the San Francisco Bay Area, and the team is distributed across San Francisco and Toronto. Some of my team members are actually in the audience, so feel free to have a conversation or ask any questions on the chat. The agenda of my talk is as follows. We'll have an introduction of Pinterest shopping and the purchase data we are using for optimization. And then we'll dig deeper into how we are doing purchase optimization using techniques like item embedding and conversion modeling. Just in case you are not familiar, here is a quick introduction of Pinterest shopping. Sorry, it's a quick introduction of Pinterest overall. So Pinterest is a place to get inspiration and ideas. Our users, we call them pinners, come to Pinterest and collect different types of content, such as images, videos, idea pins, or products for various use cases and organize them into boards. In the picture on the slide, I'm showing some of my own boards. This year, we have launched creator features. People can create content on Pinterest. Creator creates idea pins, which are multi-page video formats. We have almost 450 million users using Pinterest across the world on a regular basis. There are various use cases, and some of the common use cases are cooking or finding recipes, fashion, such as what to wear for certain occasions, such as wedding, home decor, how to decorate living room, gift ideas, and many others. One thing to notice here that these use cases are not entertainment use cases. These are very unique to Pinterest. People come to Pinterest to gather inspiration and ideas to improve their real life. And naturally, many of these use cases have underlying shopping intent. For example, when a user finds ideas to decorate their living room, they start looking for maybe a specific furniture or a wall or maybe a lamp to buy to decorate their living room. There are various ways Pinterest helps users to find inspiring and relevant products. We have many recommendation feeds or surfaces. Some of the major ones are home feed and more like this. So when a user opens our app or our website, the default recommendation feed they see is called a home feed. When a user taps on an image or a pin and then scroll down, they find more like this recommendation. In each of these recommendations, we show products when it is relevant to the user. These recommendations are very large-scale recommendations, fully personalized, serving hundreds of millions of users on a daily basis. On these recommendation surfaces, we mix products and non-products like other content like images or videos together. We also have surfaces where we only show products, such as shop search. When a user searches for something and they click on the shop button, they find products relevant to the query. Another unique way to shop on Pinterest is shop the look. Here we use advanced computer vision technology to make most images on Pinterest shoppable. So on many images on Pinterest, user can tap on an individual object in the image and see products that look similar to that object. And then we have shop similar recommendation, which shows similar products on a product detail page. And not only just product recommendation, there are some advanced way to shop on Pinterest, such as we have virtual try on, where a user can try on a beauty product like lipstick and see how they look on that product. With all these shopping features, shopping in Pinterest is already quite popular and growing. Here are some of the stats. So shopping features are live on 16 countries, including Canada. We have tens of thousands of merchants, including Shopify merchants on our platform. Our pinners, the number of pinners engaging with shopping features has increased 200% over the last 1 year. Product search or shop search has increased 100% over the past year. And there are some studies which shows shoppers on Pinterest have 85% bigger basket size compared to other social platforms. At this point, you might be thinking, well, users can discover products on Pinterest, but they can really buy on Pinterest? They can. We are experimenting with what we call native checkout. For certain merchants, they can do the checkout on Pinterest. But for most merchants, the actual purchase takes place on a third-party website. When a user finds the products and clicks the visit button, we redirect them to the retailer website or the third-party website where they can make the purchase. And if the purchase takes place on the third-party website, do we get to know? Yes, we do. We have many merchants which are our close partner, and they share this purchase data with us using cookies or other mechanism. So now once we receive a purchase event, we use a last touch attribution to find the last pin interacted by the user to attribute that purchase. This is called attributed purchases. And this data is already pretty big. Last year, we drove almost $25 billion revenue through attributed purchase for our partner merchants. And this data is not just big, it's a gold mine for machine learning. We can use this data to improve our shopping experience. One straightforward thing to do is use this data to improve our recommendation quality. Currently, Pinterest recommendation, or traditionally, Pinterest recommendations are optimized for on-site engagements such as clicks or save. The question is, how can we use this purchase data to recommend shopping content that users are more likely to buy, not just click? It is not straightforward though. There are several challenges in using purchase data and optimize for purchases. First, we have many different recommendation surfaces. And each of these recommendation surfaces has their own technology stack. So that means we have to make changes on many different technology stacks, which will take a lot of time. Another problem is there are many different actions on Pinterest, such as clicks, save, 10-second video play, creator followers. These actions are also positive actions or good actions. So we cannot forget about all these positive actions and just focus on purchase optimization. The third problem is on surfaces such as home feed, we mix different content, and each of these content has their own objective. For example, for image, we want to optimize the save. For videos, we want to optimize it for 10-second play. For idea pins or creator-created content, we want to increase their followers. And all these objectives are not always line up. And finally, another problem for purchase optimization is purchase data is sparse. It is way more sparser than any other on-site engagement, such as click or save. Less than 2% of our clicks leads to purchase. And the fraction of impression that leads to purchase is even smaller. So in this talk, I'll share how we are addressing some of these challenges. But before we go into that, let's look at how a recommendation system works. At its core, the recommendation system has two of these big blocks. One is called candidate generator. Given a query pane, the candidate generator's responsibility is to retrieve few hundred or maybe 1,000 pin from a corpus of 100 million or more. And the second block is the ranker, which uses more sophisticated machine learning algorithm to score and rank this item. And finally, the top 10 or top 20 items from this rank list is displayed to the user. Now on Pinterest, there are many different recommendations, and each of them has their own candidate generator and ranker. In some cases, the candidate generators are shared across different rankers, particularly the shopping candidate generator, because we recommend products on different surfaces. So the rankers of all those surfaces uses the shopping candidate generator. Now, given this architecture of the Pinterest recommendation systems, we propose two changes to include purchase optimization. First, we took the embedding-based shopping candidate generator, we call it item embedding, and optimized that for purchases. Second, we introduce a conversion model which can predict the conversion score of a given pin, and now the ranker can use that score to come up with the final score of the item to rank. We'll go into each of these two blocks in the next section of the talk. Let's start with item embedding. At a high level, here is how embedding-based candidate generator work. Given a query pin, we represent the query pin using an embedding. And then we have the items in our catalog. We represent those items also using embeddings. Now we use the query pin embedding to query the item embedding database. This is called approximate nearest neighbor search. And to do that, we use a standard library called HNSW. But we use our own custom techniques to create the query pin embeddings and the item embeddings. For query pin embedding, we are using graph stage or graph convolution neural network. This is a work came out of Pinterest. This is a very seminal work and used across the industry. This technique leverages the unique pinboard graph we have in Pinterest. The way it works is, given a query pin, it does a random walk over these pinboard graphs and gets top N or top 50 neighboring pins. Now this query pin and all the neighboring pins are represented in a feature space. The features are typically generated from the image and the description of the pin. So now these query pins and the features of the neighboring pins are fed to the graph convolution neural network, which creates the graph stage embedding. We use the graph stage embedding as the embedding of the query pin. We could have used the same embedding to represent our items on the catalog. But items has more information. For example, typically a product or item generally have more than one images. It has more attributes such as color, size. It has more well-defined title and description. And most importantly, we want to introduce our purchase optimization into item embedding. So instead of using graph stage embedding, we create the item embedding in a different way. We use a transformer encoder to generate the item embedding. So we take all the different item features, the different images of the item text, and then also the neighboring pins from the pinboard graph, and use that as an input to the transformer encoder. For item images, we use the corresponding graph stage embedding. Similarly, for neighboring pins, also we use the graph stage embedding. For item text, we use the text embedding. So all this goes into a transformer encoder, and it creates the item embedding. You might be thinking the transformer is generally used for sequence-to-sequence model. Where is the sequence here? Yes, there is no sequence here. And we are not using the full transformer encoder and decoder. We are just using one transformer encoder block. We observed The transformer encoder is a general architecture and creates very high quality embedding. One reason is it has this attention module, which helps modeling the interaction between the features. And therefore, we don't have to hand tune or hand create the interactions feature. The attention model takes care of that. The way we train this transformer is using our historical engagement data. From our historical recommendation, given a query pin and recommended pin, given a query and recommended pin or recommended products, where we have a positive engagement such as save and long click, we use that as a positive example. And here we introduced our purchase data or purchase related actions as positive examples. So in the positive examples, we also include add to cart and checkout. And then we randomly samples from some negative examples. Here, the negative examples are the query pin and the recommended products without any engagement. Then we create a mini batch of these positive and negative examples and input that to the transformer. Transformer creates the embedding for the positive example and negative example, and then it minimizes the loss of the distance from the query pin to the positive example versus the distance of the query pin to the negative examples. There are several advantages of generating item embeddings in this way. One is this architecture is able to capture all the nuances of the item embedding, the different images it has, the different attributes it has. Also, we are able to do multitask learning and learn from all different positive actions. And there we are able to introduce the add to cart and checkout, the conversion related action. And finally, the way we define the loss function, the distance from the query pin embedding, ensures that this item embeddings is in the same space as the graph stage embedding. That is a huge advantage because now we can query our item embedding database using any pin which may or may not be product, because any pin on Pinterest has the graph stage embedding. So that means we can use the same item embedding candidate generator for different recommenders. For example, for shop search, the query pin is a product. Sorry, shop similar, the query pin is a product because we show shop similar recommendation on product detail page. But for home feed, the query pin is previously engaged pin, which may not be a product, but we can still use the query pin and the corresponding graph stage embedding to retrieve items from this embedding candidate generator. Let's look at some result. So when we replaced the graph search embedding with the item embedding as we just defined, we saw huge gain in the conversion metrics. The proportion of users with purchases went up by 6.7%. Average checkout per user went up by 8.3%. That was all about item embedding. Now let's look at the second block, the conversion model. The goal of conversion model is to predict the probability of checkout for a recommended pin. That means is predicting probability of checkout given an impression. But we don't predict that. We found that's a much harder problem to predict. So we break that probability into two parts. Checkout given click is click given impression times checkout given click. And we found it is easier to model checkout given click. The reasons are the data is less sparse. As I mentioned earlier, checkout given impression is much sparser than checkout given click. Another thing is we are assuming conditional independence. When a user clicks on a product and then whether the user will buy or not is independent where the user saw the impression. So that's when checkout given click is independent of the recommendation surface. And that means we can use the data from all different recommendation surfaces to model this probability. And we also can use the same probability model across all these different surfaces. How do we predict the P of click given impression? Luckily, this probability is already predicted by Ranker. So all we have to do is just predict the probability of checkout given click, and which is a binary classification problem. So we use our neural network and our historical data to predict checkout given click. In our historical data, we take all the items, all the products that has been clicked. If there is an attributed purchase to that product, that becomes a positive example. If there is no attributed purchase, it's a negative example. Naturally, there are far more negative examples than positive examples. So we downsample the negatives and then use that training data to train this network. Here are some top features: the pin embedding, the graph search embed, or the graph search embedding, user embedding, the past interaction of the user to the pin, some context of the recommended surface, and also the past performance of the pin in driving conversion-related actions such as add to cart checkout. These are the top features. We have to do one more thing. We have to calibrate the probability scores against two positive rates. One reason is we are heavily downsampling the negative, and we are using a simple numerical calibration uh, to address the negative downsampling and calibrate the model. So now that we have this model, we can predict the probabilities of checkout given a click, or we predict the probability of checkout for a given pin. How we use that in our ranker? Typically, a ranker at Pinterest is a deep learning model with multiple heads. Here, each head of that model predicts probability of an action. Actions are save, click, long click. And then on top of that, we have an utility layer which combines this probability of actions using a weight. It's a linear combination of this probability of actions. So given this architecture, and finally, this utility score is used to rank the item. And given this architecture, it is really easy to use or to introduce the conversion score. Checkout is just another action. Checkout is just another action, we can add the term, the probability of checkout given impression with an weight in the utility layer and compute the final score of the item. And we hand-tune these weights using experiments. It's become a little bit complicated for home feed because home feed not only shows product, it shows other contents such as images and videos. It has a little more complicated logic of boosting the content, the new content or fresh content. It has a penalty for lack of diversity. But even though the formulation is a little more complex, at the core, it is still a linear combination of this probability of action. Given that, we can introduce the checkout action and the probability of checkout score in the same way as we did earlier for the shop similar recommendation. When we added this conversion score on shop similar and home feed, we saw a huge increase in attributed checkout and purchase. On shop similar, we saw more than 20% increase in checkout and GMV. On home feed, the gain is a little bit lower. The reason is home feed shows product, but also shows a lot of non-product content. But still, the gain is more than 10%. And this is an ongoing work for us. We are adding the conversion model on other surfaces, such as more like this or search. And we are also working on improving the conversion model. We are exploring adding more features. We are making the conversion model itself a multi-head model to predict not just checkout, but other actions such as add to cart, sign up. We also have some other type of content other than product that drives purchases, such as shoppable idea pins, native checkout content. We want to model those, their conversion probability as well. So that was all about how we do purchase optimization. To summarize, we introduced purchase optimization across different recommendation stacks with minimal changes. And we showed that item embedding and conversion model are the two key components in our purchase optimization. And we observed often double-digit gains in attributed checkout on GMV on different surfaces. But for us, we are just starting. There's a long way to go. The reason is there is a shift going on how people shop online. Today, people shop online on e-commerce website. Sometimes they use different websites for different categories of purchase. For example, for home decor, maybe it's Wayfair. For fashion, it could be different website. At the same time, users today typically spend most of their online time on social platforms such as Pinterest, Facebook, or TikTok. And these social and discovery platforms are more and more offering shopping features. And retailers are totally okay with that. The retailers really don't care from where their customers are coming from. They are okay if their customers are coming from the social platform as long as they get a sale. So, given that, and given the win win situation with the retailer, I believe going forward, more and more shopping will take place from the social and discovery platform. And this is not just a change in which website or app a user uses to shop. This enables or unlocks new applications such as creator or influencer driven shopping or live stream shopping, which is already pretty big in China. It is $125 billion business there. And with these new use cases, it will generate more sales for the retailers. And in this ecosystem, Pinterest has a unique advantage to be the leading social and discovery platform for shopping because many of its use case has natural shopping intent. Overall, driving purchases from social and discovery platform will be an interesting problem to study in the coming years. I want to thank you all for attending this talk and for your attention. And also, I'd like to take this opportunity to mention Pinterest has an engineering office in Toronto. We are hiring a lot, particularly shopping team is also hiring a lot there. So I would recommend you take a look at that. Thank you.
Thank you, Somnath, for the insightful talk. We'll go to the Q&A session now.
Sure.
I think Christopher has answered a couple questions already. We'll go to a question from Sherwin. In your opinion, what is the advantage in using Graph Sage compared to self-supervised learning embedding spaces such as variation autoencoder, SimCLR?
So main advantage of GovSage is modeling the relationship of a pin with other pin. So that graph or the network gives us additional information. If the two pins are connected, well connected, that means they are similar. So that's real like a that's very useful information to model. Now, graph search is the first version of the model. That's how we model it. But I believe going forward, you might be able to use autoencoder. And as I showed, we are using transformer encoder to model those. So I think the architecture will evolve, but the information that graphs presents is very useful and very important to model.
Okay, thank you. Next question from Morteza. What was the older solution for the recommendation engine before introducing GNN, CNN, etc.? Where do you run these models? On-prem infrastructure or on public cloud?
Yeah, very good question. I think this is an evolutionary journey. Recommender system has been studied for more than 20 years now, and it is still evolving. So many new things are coming. As we saw, this multi-objective optimization today, as we talked about, how do we introduce new objective and all. So as you go older, the recommender system, like if you go even like 10 years back, the collaborative filtering, matrix factorization was the primary way. Then we had like some previous past engagement based on the once the site becomes big, when you have a lot of users, use the historical engagement. It generally calls some memoization techniques or nap boost. So you can just remember for your top pins or top queries what the user previously engaged and use that. And then you can have a simple GBDT ranker as well. Based on your historical data, you train the GBDT ranker. And then with this evolution, this GraphSage, this CNN, GraphSage, and all these things coming in, I would recommend Pinterest has a paper. We published that paper, The Evolution of a Recommender System, which nicely shows that we started with a 3 people team and how it used to look and how it evolved. And as we can see, it is still evolving a lot in a very fast pace. And to answer your second question, we are on AWS, so we use the in terms of our infra AWS, but that's kind of an understatement. At Pinterest, most of our technology stacks has like a customization in house. We have our own ML platform. Even our like the databases or the big table, the big query table, the key value store we have, a lot of customization we have on top of that. So in a sense, okay, we are using the AWS infra, but a lot of this tech stack is kind of in-house build.
Okay. Now, follow-up question was, how did you compare the old solution with your new solution? Any A and B testing?
Absolutely. We do a lot of A/B testing, A/B testing. That's one advantage of Pinterest with this 450 million users. we can learn, we can run A/B test, and it's very quick for us to get results. Typically, we get results in few days to see whether the new model is performing better than the old model. And not just the user, Pinterest has a lot of tools to help us to run the A/B test. We have dashboards and all to, so it's pretty easy to run A/B test. It's pretty easy to get the metrics, and all these users help us to learn what's working, what's not working.
Question from Suleiman. What are 2-3 metrics that you used other than CTRs and conversions for KPIs?
Yeah, I think CTR is one metric, but for shopping, as I shared, we look at like a checkout user, GMV per user. Click-through rate is still an important indicator of the quality of the recommendation. Pinterest is also big on save, like people repeat, save on the content on their board. So that's another metric we look at. At an overall Pinterest level, we deeply care about the users coming to our platform on a weekly basis. We call it WOW. We share externally our monthly active users. So those are our core metrics. So we keep an eye on those. That should not go down. Ideally, that should increase. But just on an experiment basis, we optimize for checkout, GMB, sometimes click.
Okay, I think Shrikant has a last one. What's the business model? It seems people click on pins and buy on other websites. People who create pins get paid. Is that the question? And do you measure which type of pins make more money?
That's a very good question. That's why I spend one slide on giving an overview of purchase data. Yeah, people click here and go to the third-party website, make the purchase. As I mentioned, we are experimenting with native checkout or Pinterest checkout. So they can check out on Pinterest platform. That's one business model. Second business model, which is the biggest business model of Pinterest, we are helping user to find the most relevant and inspiring product. So we are solving a use case for the user. The more the user uses it, there are many monetization opportunity. One we are leveraging currently is ads, and it is already a pretty big business. We are already like a $50 million on shopping ads revenue. This year, we are projecting it could be like a multi-$100 million business. So we will monetize our native checkout. We are already monetizing our ads. So, and then going forward, maybe affiliate marketing. So there are different business model will evolve. But we believe like if we help user to find the most relevant content, we drive the use case, and the monetization will be easier. Shopping is like a $4 trillion business. So monetization is the easiest part as long as people use it.
I'm sure. I think we reached the end of the session. On behalf of TMLS team and everyone here, I would like to thank you, Somnath, once again. Thank you for your time and attention.
Thanks, everyone. Thanks for the talk. It's really a pleasure to be here.
Thank you.
Thank you.